In 1990, Paul Smolensky introduced the concept of the tensor product representation, which aimed to bridge the gap between connectionist, neural network models and symbolic processing in the field of artificial intelligence. This paper had a significant impact on the study of neural networks and cognitive modeling, providing a framework for integrating distributed representations and symbolic processing. His paper begins by acknowledging the strengths of connectionist models, which excel at parallel processing and learning from examples. However, it also highlights the limitations of these models in representing symbolic knowledge and performing systematic operations. On the other hand, symbolic systems are good at representing and manipulating structured knowledge but struggle with learning from raw data. To address these limitations, Smolensky proposes the tensor product representation, which combines the strengths of both connectionist and symbolic approaches. Tensor product representation aims to capture the structured nature of symbolic knowledge, while leveraging the distributed nature of connectionist representations. The core idea behind tensor product representation is to represent symbolic entities using distributed vectors, tensor products. Smolensky describes how symbolic entities such as words, concepts, and relations can be encoded into high-dimensional vectors in a way that preserves their structure and relationships. These vectors can then be manipulated using mathematical operations. The tensor product representation framework is built on three key principles. 1. Compositionality. Tensor product representation enables the composition of distributed representations using tensor product operations. By combining the vectors that represent individual components, it becomes possible to represent more complex structures and relations. 2. Binding. Tensor product representation allows the binding of distributed representations. Binding refers to the process of combining multiple representations into a coherent whole. Smolensky introduces binding operations that enable the integration of different components into a single distributed representation. 3. Systematicity. Tensor product representation exhibits systematicity, meaning that the same operations can be applied to different elements in a consistent manner. This property enables the systematic manipulation and transformation of symbolic structures encoded as distributed representations. Smolensky provides examples to illustrate how tensor product representation can be used to represent and manipulate symbolic structures. He demonstrates how tensor product operations can capture the hierarchical structure of linguistic expressions, and how the binding operations can combine different constituents into coherent representations. The paper also discusses the advantages of tensor product representation over other connectionist models, such as the ability to represent and process hierarchical structures, the systematicity in operations, and the preservation of structure and relationships during composition and binding. Smolensky further explores the potential applications of tensor product representation, including its relevance to linguistic theory, cognitive modeling, and the representation of semantic networks. He discusses how tensor product representation can capture semantic relationships, encode hierarchical syntactic structures, and model aspects of human cognition. The paper concludes by emphasizing the significance of tensor product representation in bridging the gap between connectionist and symbolic approaches. It highlights how tensor product representation allows for the representation and manipulation of symbolic knowledge using distributed representations, offering a promising path for integrating connectionist and symbolic processing in AI. In summary, the tensor product representation provided a framework for integrating connectionist and symbolic approaches in AI. Smolensky demonstrated how tensor product representation enables the representation and manipulation of symbolic knowledge using distributed representations, allowing for compositionality, binding, and systematicity. This paper had a profound impact on the field, influencing subsequent research in neural networks, cognitive modeling, and the integration of symbolic and connectionist processing in AI systems.